that here. So we have the temperatures, x1, x2, all the way to xn. And one implicit assumption we're making with this sort of model is the data points are independently and identically distributed. So you can imagine that sort of assumption doesn't really make sense when we're modeling temperatures, because the weather the next day probably depends on the weather the previous day. And hopefully weather generally gets warmer as we approach spring and summer. But for the sake of this class and for maximum likelihood estimation, we're going to make this IID assumption. So what we do now is we write down the likelihood in terms of the parameters, theta, where theta actually here is the mu and the mean, which is mu, and the sigma, which is the standard deviation. And this is the product of a bunch of different terms, right? So for each of our observations, we want to write down the probability that observation occurred. So the key difference between each of these terms is you put in the actual observation you've seen. So we have this xi minus x sub I minus mu squared term. Okay, and then since taking the derivative of this expression is kind of complicated, what was the thing we did last time to make it easier? Yeah. Yeah, you can take the log of the entire expression. So we're focused on mu first. We'll just take the partial derivative with respect to mu. So arg max L of mu is going to be equal to the log, which we used lowercase l to write last time. So that's, if you take the log of the entire expression, the product just becomes a sum of terms instead. So we have sum I equals 1 to n. And one other thing to note is this term goes away when we're taking the argmax over mu, because there's no mu in 1 over 2 pi sigma squared. So we can just throw that away. It's a positive constant. The point of it is really to make sure our probability density integrates to 1. So instead, we just have log e to the xi minus mu squared over 2 sigma squared. So we're trying to maximize this expression here. Log and e actually just cancel each other out because they're inverse operators, right? So we're just left with a sum. And what should we do next from this expression? Yeah. Yeah. Yeah, great. So we can pull out the 1 over 2 sigma squared. This is actually also just a positive constant. And if you're trying to maximize x versus maximizing 3x, the argument that maximizes that expression is the same. So we can throw away that term as well, actually. So we have argmax over mu, I equals 1 to n, and just xi minus mu squared. Okay. So this basically actually just means what we did is we took this product of bunch of Gaussians, which looks pretty complicated. And if you go through each of these steps, like pulling out constants, taking logs, it's saying what we're really trying to do is trying to find a center point that minimizes the sum of a bunch of these terms. So, I actually made a small mistake here. So there's a minus sign in front of all of these terms. So that's pretty important to carry out throughout each of these calculations. Okay. sorry. So if you're trying to argmax a negative expression, that's the same as trying to minimize the negative of that expression, right? So you can write this as argmin mu I equals 1 to n xi minus mu squared. So we're trying to minimize, we're trying to pick mu to minimize the sum of a bunch of these squared terms. And you can take the derivative now, right? So if we take d by d mu of our likelihood expression, we get 2 I equals 1 to n xi minus mu. And we're just going to set that equal to 0 to find what the best choice of mu should be. So if you just move the mu term to the other side, you get I equals 1 to n x sub I equals n times mu. Since mu is just some constant we're trying to estimate. So finally, you can simplify this to mu equals 1 over n. So the interpretation of this is if you're trying to estimate the temperature and modeling it with a Gaussian distribution, we should just take the average of all the temperatures we've seen so far. So maximum likelihood usually gives you a pretty intuitive answer, and you can see that's the case here. We're just taking the average of all the temperatures we've seen so far. Yeah.
This works, the likelihood works for both mean and sigma, but is sigma going to be as intuitive? Because like it makes sense that the average of like the mean temperature is just the sum of all the temperatures divided by the number of temperatures.
Right.
But the distribution would be slightly different.
Yeah, you actually do something similar to the sample variance. So like you can estimate how far each of the points is from the mean and then scale. Yeah. So we won't do that here, but if you look it up, you can find a derivation. Yeah.
Can you just explain the first step again? So how can you get that? Because I was looking at when we did for the coin flipping.
Yeah.
Coin flipping was there was the probability of it, or rather the expected value of it was like based on like how many heads or tails we flip. So like what is it here represent?
Yeah. So here our data is our sequence of temperature observations. Whereas in the coin flipping example, we had a bunch of heads and a bunch of tails in our sequence. So our likelihood before was like something like this, where n sub h and n sub t are the number of heads and the number of tails. Does that make sense?
Right. So what is that one over here?
What is the one on the one I just?
No, the one left. Right.
Yeah. So this is saying that we assume we have like the same model, which is a Gaussian model for what the temperature looks like. And we're looking for the probability under a Gaussian model of getting that particular x sub I temperature. So like on day 1, if we observed negative 2.5 degrees, what's the probability if you have a mu and a sigma of seeing negative 2.5 degrees? Yeah.
The maximum and the minimum temperatures have different distributions, right?
Yeah.
Okay, so you have to do this 2 times?
Yeah, so today we're actually going to be talking more about multivariate Gaussians, so you can actually do this in one step. I mean, if you repeated the process with the minimum temperature, it's going to be the average of all the minimum temperatures too. So we'll learn how to do this like with vectors to do it in one shot. Any other concerns? All right. Yeah, I think it was good to work through this example because we'll be talking about Gaussians for most of this lecture once we finish up the remainder of the probabilistic modeling part. And it's just another good example to work through. Okay. So, back to. Okay, so we're going to continue off from where we left off. I guess before we begin, some announcements. So some of the office hours just got released on Piazza, and there'll be more coming up, so you can check that schedule, and if you have questions about the project, it's probably best to go to project office hours. I think Chandra and I are probably better at helping with the open-ended projects, so you can come to us for that. The project office hours are the best place for project help, and there's also a video tutorial. So in past semesters, a TA had a short tutorial on like an overview of the option 1 for the project, and I posted that link on the recordings on the pinned Piazza post. So you can look for that if you want some guidance on option 1. I think we had a decent number of people choose option 2, and one thing to note, I guess, is if you find option 2, the open-ended project, to be too hard, like you're having a hard time getting your data, you can always switch back to the first option as a fallback option. So you aren't penalized for trying something more ambitious. Okay, so that's number 1. Homework 3 will probably release tomorrow. And this will be due a week after the project, so you have some more time for that. Most of what you need should be covered by the end of today's lecture. Yeah.
For option 2, do we have to wait for our proposal to be approved?
Yeah, well, you don't. You can just go ahead, but we'll have feedback like within a day or 2 as well. And I think that's pretty much it. Yeah. So I guess one good thing about some of the topics we're covering now is there's broad overlap with statistics, and a lot of the textbooks that we linked and other courses around the universe have classes or tutorials on these topics with a lot of problems. So if you find these topics hard, you can always look for more problems, and that's probably one of the best ways you can learn.
So for, like, we chose the second option.
Mm-hmm.
For the project proposal, like, when can we, like, will we get any feedback for it, or do we just say here's?
Yeah, well, you'll get feedback probably by the end of tomorrow. It's like
on Marcus?
yeah, through Marcus. Yeah.
Okay.
Yeah. Cool. Yeah. Any other admin questions? Yeah, I guess as a general meta note, this is like the time of the year I feel like it's kind of hard because winter is long, so just make sure you take care of yourself, cover all the necessities like sleep, food, and so on. But it's important to maintain like motivation throughout this period. Okay, so we'll talk about Bayesian parameter estimation now. This sort of deals with one of the issues that you see when you're doing maximum likelihood estimation, which is that maximum likelihood estimation only uses the data. So we have a problem where if you have too little data, you often get inaccurate estimates. So if we return back to the coin flipping example, if you flip a coin twice and you get heads twice, then the maximum likelihood estimate for the probability of heads is going to be equal to 1. So when you don't have that much data, maximum likelihood can give unreasonable answers. And we'll talk about 2 potential techniques to address that. Yeah, did you have something?
Can the data be bootstrapped with all this?
What
Can we bootstrap the data with all this?
What do you mean by bootstrap?
Like free sampling from the distribution.
Yeah, I guess we don't have a distribution, right? Like the data is just what we observe. Yeah.
So how about the point of Bayesian, like statistics that should have like data? So let's see what makes sense that there's distribution.
Yeah. Wait, so what was your overall? Oh, okay, yeah. Yeah, so I guess the Bayesian approach is gonna try to basically have some sort of prior assumption on what the distribution looks like, and then that prior will help us avoid this pathological case. So the rough idea of the Bayesian model is previously we assumed theta is some fixed quantity for maximum likelihood estimation. And what we're going to do now is we're going to treat theta as a random variable as well. So what that means is theta also has some underlying distribution. And sort of the Bayesian viewpoint is you have some prior idea of what your model parameter looks like. You observe your data, and then you update your prior belief to a posterior belief on what the distribution over the random variable looks like. So overall, we need two terms here. We need the prior distribution P of theta, which encodes our belief, and then the likelihood, which measures how likely the data is under our given the setting of the parameters. And the overall way you compute the P of theta now is we use Bayes' rule, right? So we have P of theta given data is equal to P of data, and the top is P of theta and data. And we can decompose it into the top term as the product of the prior times the probability of the data given the theta value. The other thing to note is you usually just never ever compute the denominator. You can get away with not doing this integral, which is really tricky to do because you're integrating over all choices of parameter values, and it's in general intractable. So we're primarily just focusing on the top term, because when you're doing like argmax or taking expected values, you don't actually need to compute the integral. So to be more concrete, we'll revisit the coin flip example. And here we already know the likelihood, so we already know the probability of the data given the theta value. From last time, it's equal to this because we're assuming the flips are identical and independently distributed. So you can multiply a bunch of thetas and 1 minus theta terms together. And sort of the tricky part of a Bayesian modeling is you have to choose a prior, and it's not quite a science. It's more you have some assumption on how the world might work or how your distribution might work, and then you choose a prior to fit that. So some possible choices of prior could be you can assume a uniform prior, so a uniform distribution over all values of theta. That's a potential prior. But we also know that most coins are generally fair, so one prior and one distribution we'll particularly focus on is this beta distribution. So the beta distribution is written out as this term here. There's this gamma thing, which you can ignore because it's a weird, complicated normalizing function. We mostly, since we're doing argmaxes, we can just focus on the theta a minus 1 and 1 minus theta b minus 1. But if you're curious, this is the generalization of the factorial function, basically. So if you take in a integer, it's going to give you the factorial function exactly. Other than that, it's mostly there just so if you integrate this distribution, which is parameterized by a and b, the integral comes out to 1. So it's a constant that's just there to make integrals work out nicely. So let's look at what the beta distribution looks like for various choices of A and B. One particularly interesting case, I guess, is when A equals B equals 1. If you go back to the previous slide, we have theta A minus 1, 1 minus theta B minus 1. So if you plug in A and B equals 1, we get theta to the 0 times 1 minus theta to the 0, and that's just equal to 1. So this is a uniform distribution over the choices of theta. And you can sort of see how different choices of A and B give different possible interpretations. So if A and B are relatively small, most of your probability is concentrated around 0 and 1. So if A and B are small, you have the blue curve. And then basically as you increase A and B, you sort of get sharper, these bell-shaped curves that become progressively sharper around the values of A and B you choose. So you can see A equals 1 and B equals 1 is uniform, A equals 5, B equals 5 gets you something that's roughly Gaussian shaped. So that's our prior. And the other property that we'll use throughout the rest of this lecture is expected value of theta is equal to A over A plus B. So the expectation is really nice. It's actually just the sum of the two parameters in the denominator and A in the numerator. And that's actually one of the reasons why we have this A minus 1 and B minus 1 when defining the distribution itself. So it's so that the expectation turns out pretty nicely. Yeah.
Does this only apply to a binomial like stuff like a coin flip, or is it only heads or tails?
Yeah, so this beta distribution, the most frequent place you see it come up is as a prior distribution for the Bernoulli random variable. But I guess in general, you can use it to specify any sort of distribution you want that's between 0 and 1. So if you pick your parameters A and B, you get a probability density function over this interval.
So will we say like A is how much we want it, and then B is like what is not wanted?
Sort of the interpretation actually is like A is a prior belief on how many heads there are, and B is a prior belief on how many tails there are. So we'll see why that is like very soon.
So like generalized to like any distribution, we can say like A is how many of the target we want, and B is like how many not the target we want.
Yeah, there is like a multivariate generalization, which is called the Dirichlet distribution. But I think since we're estimating theta, that's focused on like the two variable case. Okay, so the reason this prior is really nice is when we're trying to compute probability of theta given the data, you'll notice that the two functions we're multiplying together have the exact same functional form, which means we can collect the terms together, right? So we have theta A minus 1 and theta to the power of n sub h. So if you combine the two terms, the exponents just add, and you get theta A minus 1 plus n sub h. Similarly, you can collect the 1 minus theta power terms together and get, it just collapses into a single term as well. So what that means is now our posterior is actually also going to be a beta distribution because it's proportional to this theta to some term times 1 minus theta to some term. So what that means is our posterior distribution is proportional to this term. And I guess in general, our posterior is some complicated function, but because we know what the expected value of the beta distribution is, we can compute the expected value of theta given the data set. And that expectation is, we're just going to use what we had from before. Given, this is like the new A, So let's use A tilde. And B tilde, our expected value is just this term here, right? Or written out, it's this term over here. So what this is saying is now we can estimate our parameters after observing the data and given our prior to be this estimate here. And this is why you can also interpret the number of heads and the number of tails as pseudo counts, because it's sort of like you just pretend you have these number of heads and tails going into before observing any data at all, and then after you observe the data, you add those actual counts to our pseudo counts. So this is a particularly nice example because the two functions have the same functional form, and in general we refer to this as a property called conjugacy, and it's called conjugate priors. Okay, so this is one potential way to estimate theta. Yeah.
Why do we have the -1 on the top?
Yeah, so it's because if you have A hat and A tilde and B tilde, the distribution you actually correspond to is this distribution. So there's a -1 that's already accounted for. Yeah. I guess the interpretation of pseudo counts is you normally don't know how to choose a prior, but one way you can think about how you choose a beta distribution prior is you pretend that you've already flipped this coin X number of times and you observed some number of heads and some number of tails. So that's how you can set the beta distribution prior. Okay, so I think this graph will sort of highlight what's going on here. So we're plotting three different things here. We have our prior distribution, which is shown in this blue curve. So this might be something like A equals B equals 3, I think. And the green curve is the likelihood we observed our given data. So we're looking at this case where we flip the coin twice and we get 2 heads. So the prior is going to be some monotonically increasing function that goes from 0 to 1. And if we were just doing maximum likelihood estimation, we're going to just take this point up here. So that's theta MLE. What the posterior is it's multiplying the prior times the likelihood and then normalizing, right? So posterior equals prior times likelihood normalized. So that's going to correspond to this red curve, which you can see if we're taking the max of the light curve, it's going to give us another estimate. We're actually going to call this estimate the map estimate. And the other potential estimate you can do is you can take the expectation over the posterior. And that's like sort of the third potential way you can estimate the parameters of your distribution. So this idea becomes, the idea of the prior is sort of more interesting if you consider having more data. So we're going to have the same prior here. It's a blue curve, but since the y-axis changed on the right-hand side, the entire curve is going to look shifted downwards. And here, the red and green are almost actually indistinguishable because we have so much data. So if you have a lot of data, the likelihood is going to overwhelm the prior. That's actually a term statisticians often use. And if you're making a prediction, you almost just look at the data. So basically what this means is in the limit, as you get more and more data, you're gradually going to forget your prior because the probability coming from the data is so large. So the red and green are the same on the right-hand side, but they're very different when you don't have many data points. Any questions here? Okay. So the idea of the map estimate is we're finding the most likely parameters under the posterior. So we're maximizing P of theta comma D. And you can decompose this a little bit by writing this as the argmax of P of theta times P of data given theta. And because we can take the log trick, you can also write this out as a sum of two separate terms. So if we wanted to compute the map estimate for this coin example, we can add the log of P of theta plus the log of P of data set given theta and take the derivatives, set them equal to 0. We'll work out another more complicated example for the map later. So overall, the take-home message here is it's actually sort of similar to our expected value estimate, except we have to subtract by 1 in the numerator and subtract by 2 in the denominator. But the overall procedure for deriving this is pretty similar to what we had before. And this is a table that shows the 3 potential estimates you can have for this coin flipping example. So this is the formula for what theta becomes. And you can see if you have very few examples, theta maximum likelihood is going to probably overfit to your actual data set. Whereas you can sort of view these as roughly regularizers, where we're regularizing towards our prior now in this Bayesian setting. So theta map is going to be 0.675, and the expected value of theta is 0.67 in this case. Eventually, as you get more and more data, so if you have infinite data, we converge to theta maximum likelihood. Because as I described before, the data overwhelms the prior. So you can see, like, if you have a lot more observations of heads, all the estimates become quite similar. Okay, yeah. So that's the end of this lecture. So there's 3 potential estimators you can use if you're using this generative approach. Any questions here? Okay, maybe we can take a break because the next section we're going to do some linear algebra review and then we'll talk about multivariate Gaussians. So it's sort of a shift. Just make sure, I guess during the break you can brush up a little on the slides for linear algebra, but I'll go over everything again. So let's just resume in like 6-7 minutes from now.